let's go for it. Let's do some reviews of radicals when you're working with exponents. Remember, when you're multiplying variables that have the same base, you can add their exponents. So here, when you have x cubed times x to the 5th, that's really x to the what? X to the 8th. Again, that's really nothing different than what we've had before. So we want to make sure we stay on top of that. Then we also have the fact when we have exponents outside of parentheses. Now, think about what that really means. It means everything that whatever in that parenthesis is being raised to that power, or that what's in that parentheses is being multiplied by itself that many times. So when you do that, you find out the quickest way of working with this is actually to multiply your exponents. It gets the same result. So when I'm looking at this one here, and I'm going to zoom in just a little bit, and I get the quantity 3x squared being cubed, that really means I'm going 3x squared times 3x squared times 3x squared, right? So we want to be able to do it quicker than that. Who wants to really write that all down? But you need to remember the number has an exponent too. That's 3 to what power right there? If I just have a 3, what power is that 3 raised to? Should be the first power, right? So when I'm cubing everything in there, I need to remember that the constant term is raised to the first power. So then I go, all right, 3 times 1. Well, that's 3 cubed. Then I got my 3 times 2. Well, that's x to the 6th. Now, when you're simplifying, when you're working with exponents, one rule is if you have an exponent with an actual number, you get rid of that exponent as soon as possible. So you go ahead and you cube 3. What's 3 cubed? So your answer would be just 27 x to the 6th. That would be your process. But remember, this could be 3 squared. Well, that would be 3 to the 6th power. Anything like that, you have to be very careful. Those two simple things. We are not going to be working really much with division here. We'll talk a little bit about rationalizing the denominator. But you have to be able to work with those two rules. Very key. Now, here's another thing. Without turning around, list as many of the perfect square numbers that you know through 20 squared. Doesn't have to be every single one. You see, some of you are reading, because this is one I know. Some of you memorized these last year with Mr. McDonald. If you know these, you can simplify radicals quickly.
You're saying how far you go?
FC is the name limit that you can get. Seriously, I think most people should be able to get through 12 squared, normally without any problem. It's after that it gets a little more complicated. All right, going through these, why do you need to know them? Because those are the things that are going to help us simplify it quicker. And obviously 1 squared's 4, 1 squared's 1, 2 squared's 4, 3 squared's 9, 4 squared's 16, you go 25, keep going through. You got 9 squared's 81, 100. 11 squared's what? 121. 12 squared? 144. Now this is when people start getting sketchy. 13 squared's what? 169. Yep, 169. And if you know 13 squared, you already know 14 squared. Because the only difference between the two is 6 and 9 switch spots. So it's 196. 15 squared, you know it's going to end in a 5. So yep, it's 225. 16 squared is going to be 256. 17 squared. Oh, this is the one that... Guys, what's 7? First of all, what's 7 times 7? 49. So you know a 9 is going to be in your units digit. And for 17, 18, and 19, all you have to do to get the next two numbers is multiply by 4. What's 7 times 4? 289. 18 squared, we know, is going to end in 4 because 8 times 8 is 64. All I have to do to get the two numbers in front, go 4 times 8. 19 squared, well 9 times 9 is 81, so I know I have a 1 here, and then I just go 4 times 9. Now that's just a quirky way of memorizing it, but it works for those three, 17, 18, and 19. And then 20 squared should be an easy one. That should be 400. So seriously, if you got over half, you can do these. You can simplify radicals. Now remember, I'm going to teach you the fastest method of simplifying radicals, which means you always pull out your greatest perfect square number. Now, there's two methods of simplifying radicals. I'm going to show both because some of you were taught different in Algebra 1 than what we're taught here at Wheatley Academy. And one of them is using prime factorizations. And that means you break it all down to all the smallest prime numbers that multiply together. And if you do that, the prime factors of 8 end up being 2 times 2 times 2. Real earth-shattering primes, I know. Then you look at it and you always look for pairs. Is there a pair of 2? Yeah, because we know that means 2 times 2, which is squared. So you take out that pair and you put it out front. 2 root 2. That's working with prime factorization. That's fine if the numbers are small. But if your numbers are big, ooh, if you do all those factor trees and all that type of stuff, or some of you do what's called reverse division. I've never understood that one. But you need to make sure you have it. Now this is the method I'm only going to use with you. It's going to be the fastest method. It's factoring out the perfect square number. 8's not a perfect square number. How do I know that? It's nothing here in the right-hand column. So I look at it and say, is there a perfect square number smaller than 8 that can come out? 4. So I know I can rewrite it like the following. I take the perfect square number and I put it in a radical to the left. What's left over goes to the radical in the right, which is 2. Now you take the perfect square, or the square root, of 4. What's the square root of 4? 2. The radical sign goes away. The one is left is the one with the root 2, which is 2 root 2. Now, what if you don't take the perfect square number, the largest perfect square number out? You might have to do that a couple times, but always pull it out that way. All right, memory been jarred a little bit, I hope, again, because this has still been a huge struggle I've seen over and over again. Let's do a couple more of these. Here for B. Now, all of these, I'm going to do both methods. I'm going to do prime factorization and perfect square numbers. Like I said, not my favorite way, but I want to make sure that everyone is on the same page. So with this will be our method 1. Star this one. This is the method I prefer. This will be method 2. All right, I get 2 times the square root of 98. Can anyone tell me what the prime factorization for 98 would be? So 49 2, but 49 can be gone in further, right? So it would be 2 times 7 times what? 7. Now looking at that, do I have a pair of 7? Yes. So then they come out. Like I had a friend describe it like that's a wedding chapel. 2 that are alike, 2 become 1. Only 1 7 comes out when you take the square root. So you get 7 times 2 times the square root of 2. Well, that's 14 root 2. How many of you were taught this way? I was just curious. Anyone got taught prime factorization? It's easier for some people to see. Is it a wrong method? No, it just takes longer. Because when we look at the next method, which is the one that I prefer, and I get 2 times the square root of 98 here, I rewrite it in my 2 sets of parentheses. The middle one is the one that I want to put my perfect square number in. What's the largest perfect square number that comes out of 98? What did you have earlier, Zach? 49. What's left is a 2. So this is the one that I take the square root of. So I get 2 times the square root of 49. Well, what's the square root of 49? 7 times root 2. I get 14 root 2. In this case, it even took about the same amount of steps. Pick which method works best for you and always own it, okay? Learn it well when you're working with it. Now, here's one. We also have to be able to do this with variables and exponents when you're doing these. Now, prime factorization with these makes a lot of sense. but it's not what I consider my favorite way of doing this. Because if I rewrote this as a prime factorization, how many x's do I have to write underneath there? So I have here 6 x's. Make sure I count the right number there. And then if I took out the pairs, this is what I'd get. One pair, so I have an x. I have a second pair, which is an x. And I have a third pair, which is what? An x. And what's left is square root of 1, which is 1, so no big deal there. So my answer is x times x times x is x cubed. Now when I look at the one on the right, I instantly know it's a perfect square number. The reason why it's a perfect square number is look at your exponent. Is it odd or even? It's going to be even. So if that's the case, I know it's a perfect square. Here's the thing. Why do I know that? What's x cubed times x cubed? Nope. We're not multiplying the exponents. What do you do with exponents at this point? X to the 6. Let's do another one here. What is x squared times x squared? X to the 4th. Oops, I have to make sure I put my x to the 4th here. Or when we have here, how about x to the 9th times x to the 9th? What do you get? X to the 18th. Notice every perfect square here is an even number. Now here's the deal. How do you go backwards then? What number is here? So what if I took the square root of x to the 18th? How would I know it would be x to the 9th? What's a quick way of doing it? Divide it by 2. And here's what I want you to do. Here's the easy way. If the exponent is an even number, divide the exponent by 2 and take out. All right, here's what I mean by this one. Let's go back up to here. Is that an even number? Okay, it's an even number. So basically, I'm like, that's even. So I'm going to go 2 divided into 6. What does that get me? 3. So that means my square root here is going to be x cubed. That's all you have to do, because that is a perfect square number. And so I'm going to write it down here. So take out x cubed. All right. Now, here's my question. What happens if I have an odd? Like which of those? Like one like that. So let's just call this another example here. Let's take the square root of, let's go x to the 9th. If I have x to the 9th, that's not a perfect square number because is it even exponent? No. But I'll tell you, there is a perfect square number I can factor out. Because is this true? Can I rewrite it as x to the 8th times x to the 1st? Is that true? Do they multiply together to give me x to the 9th? Okay. Now, all I did is factor things out here. Really what I'm doing is x to the 8th a perfect square number. So basically, I know I have the square root of x to the 8th times the square root of x. I can drop the 1 because it's understood to be there. What's the square root of x to the 8th? You take your exponent and divide it by what? 2. So that's x to the 4th root x. If you have an odd number, you're going to leave a variable it to the first power inside. Unless it's x to the first place, and then you don't ever take it out. Should we try another one of those? Or do you want to actually see it worked out in the next problem? The next problem will show you how to do it. And then we'll do some extra ones on here. Now, let's do D. We're going to skip method number 1 for right now. because I really don't want you doing prime factorization on this one. It takes too much time. Instead, I want you to come over here and look at this and think into my two sets. I want my perfect square numbers. I want my non-perfect square numbers. Okay? So looking at that, look at 75 first. Is there a perfect square number that comes out of 75?
Yes.
Which one? 25. So I put a 25 here, but what goes in this one over here? 3. And then remember, 25 times 3 is 75, so we know that works. And then I look at my next value. Here I have x to the 5th. I need a number to be what in order to be a perfect square number? I need it to be even. So I take 1 less of that. What's 1 less than x to the 5th? That's x to the... So I put an x to the 4th down, and then what do I have left over here? X to the 1st, right? X, right? Then I look at y to the 4th. It's an even exponent. So does that go into the left one or the right one? Let's put the phone away, please. It's going to be the one on the left, right? Because it's even, so it's y to the 4th. Now I should be able to take the perfect square number of every one of these. What's the square root of 25? What's the square root of x to the 4th? X squared. And then what's the square root of y to the 4th? Y squared. And then what comes along is what's left on the right, square root of 3x. All right. Did that jar some memories from Algebra 1? Yeah. Because the thing is, next year you're going to get cubic roots and fifth roots that you're doing this for. So we have to be able to understand this process for just a simple square root. Now, I'm going to show you the prime factorization method that, to me, it's boring. It takes too long. Because if you rewrote this, you end up having 5 times 5 times 3 times 5x's times 4y's. And then you just start looking for the pairs again. Oh, I have a pair of 5s. There we go. 3 gets left alone, does it not? I get a pair of x's. Great. So I got times x. I got another pair. Times x. This one has to be left alone. No pair. And then I get pairs of y's. So times y. Times y. And then I rewrite this knowing what's left, what's underlined here. A 3x. Then I combine all my terms here and multiply it together. I get 5x squared, y squared, root 3x. I don't know about you, but I definitely prefer the method on the right. Because if the numbers get really large and nasty, the one on the right saves time. Now, there is only one extra thing I'm adding on here, but it is not on your homework. Did everyone just hear me on this? This is just something I need to remind you because you have special right triangles on your final, and it's going to be there. Rationalize denominators. Always make sure there is no radical on there. So remember, rationalize denominators. That's one of those things that if you remember now, it just makes it easier for next year. So for instance, an example that I have for this was something like 4 divided by the square root of 3. I want you to simplify that. Or maybe I actually had you go from long leg to short leg on a 30, 60, 90 triangle. This would be a process. 4 divided by the square root of 3. Can I leave the radical there? No. We have to rationalize it. And you learned last year to do so, you multiply the numerator and denominator of the fraction by the radical in the denominator. Now notice, really what number are you multiplying by, guys? You're really multiplying by number 1. Root 3 divided by root 3 is what number? 1. So you're just changing looks, not values. So when I do this, I multiply it across, I end up getting 4 root 3 all over 3. Because when you square a square root, which is what you're doing here, you're squaring a square root. That's the same thing as the square root of 9, which gives you 3. When you're done, though, always double check. Can I simplify and reduce fractions even more? No. So that would be your correct way. So I'm going to actually write this out in front so you remember what the process was when we're doing it. Rationalize denominators. Do not forget. I will say right now, you're going to have to do that on the final somewhere. So make sure you know how to work with your 36 and your triangles and be able to work with these. All right.